Just as a refresher, last class we started 3.3, which is all about dividing polynomials. And last class, over the method that we said we're really not going to use for the rest of this course, which was long division. Now, I did mention that it's a great method. It has its uses. But for the thing that we're going to need to do in this course, we're going to defer to synthetic division. Now, I want to go ahead and point out that you might think after going through this synthetic division and doing dozens and dozens and dozens of them and getting used to them, you might go, well, why would we ever go back to long division? Because long division always works, and synthetic division is only going to work for a very, very small set of cases. However, with this course, what we want to do is going to be that specific case. So for our goal, synthetic division is always going to work. But again, when you go to other types of problems where maybe you're just simplifying a fraction that can't reduce or factor and reduce, then you would have to go to long division because the synthetic division method might not necessarily fit the format. All right, so we saw a couple problems. We went through them. I'm not going to do that again. And we just kind of left off at showing the instructions of synthetic division for maybe a half a second, not really enough to get into. So let's go ahead and show what that process is. Let's talk about it for a few minutes, then let's practice, 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 practice it. And we are going to practice this a lot. So in order to do synthetic division, that's what this first if is about. For it to even work, which I said for all of our intents and purposes it will, but for it to actually work, the denominator has to be just x and a number. That's what this is really saying. That's what I'm trying to emphasize here, that it's just a variable and a number where the variable has to be linear. You can't have an x squared or an x cubed or a square root or an absolute value or any weird stuff. And there can't be a coefficient in front of x. So I'm talking about things like x minus 2. If that was the denominator, then we could do synthetic division. So it doesn't matter what the top is, it's all about the bottom. So we could do synthetic division on that, or x minus 1,000. Doesn't matter what the top is, we could do synthetic division with that. Now you see this minus and you might be thinking, oh, well, that means it's always got to be a minus. No, it's just, this is kind of us getting used to that whole things going in opposite directions. And that's going to be a continued issue, so that's why they have a minus here. But it can certainly be anything over x plus 5 or anything over x plus 10.3. It doesn't even have to be a whole number. It can be a decimal, it can be a fraction. We try and avoid that if we can, but it can certainly happen. Again, the point is you can't have a number in front of the x. If this was 2x minus 2, we couldn't do synthetic division. If this was 5x minus 2, we couldn't do synthetic division. It has to be x and then a number. Not 2x, not 3x, not 5x, just an x and just a number. No x squareds, etc. So what are we going to do? This is the process down here. This is our process, and it looks really long, but when you actually get to doing this, you're going to be able to just go boom, 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 boom. Looks like a lot more detailed than the actual work. Write C in a half box to the left. Now this half box thing, this is just my own notation. I've seen, and I don't want to say just my notation, but a lot of common versions of the notation. Some people will put it in a whole box. This would be a whole box. So when I say a half box, this is just how I was taught to write it. This is how most of the textbooks I've seen write it. So that's what I'm calling a half box. And then you put that number, whatever this was, in that box. Now if this was a minus 2, then a positive 2 goes here. That's what this minus is trying to emphasize, that the number in the half box changes sign. So for this first one, it would be a positive 2. For this one, it would be a positive 1,000. For the third one, because that says plus 5, we'd be putting a minus 5 here. And for the last one, because that says a plus 10.3, we would have been putting a minus 10.3 there. So again, this number's sign and whatever goes here will be opposites. So to the right of this half box, you're going to write the coefficients of the numerator, including any zeros. So we talked about with the long division how if you didn't have an x squared term and an x cubed term, you needed a 0 because it was a placeholder. That same principle holds here. But we're only going to write the coefficients. These are just the numbers not the variable. So something like x squared plus 5x plus 6, all we would write is 1, 5, and 6. If it was x squared minus 5x minus 6, we'd write 1 minus 5 minus 6. So all we're doing is writing the coefficients. If I had x squared minus 9, I'd go 1, 0, and minus 9. 1 for the x squared, 0 for the x not seen, and then the negative 9 for the minus 9. Now, we're not changing the signs of those. It's this part, this is the only thing that actually changes signs. The C, the thing from the bottom. Then after that, you're going to leave a blank row below and draw a line straight across under the blank row. That's just like the adding or subtracting part from long division. So what I'm saying is you're going to end up having something like this, some half box where your C is there. You'll have your coefficients of the polynomial here. So you'll have a number here, a number here, a number here, and it could be 3 or 4 or 5 or 10 of these numbers. You leave some blank space here, and then you just draw a line below it. And some people like to put a plus sign there. You don't have to, but it will be implied otherwise. So write the C in the half box. That's this step. Check. Write the coefficients to the right of it. Check. Leave a blank row, draw a straight line under it, and a plus sign. Check. So that's what we've done so far. Then what we do is bring down the first coefficient. And when I say bring down, I mean under the line. We're bringing this down because there isn't going to be a number under it. So this number just gets brought down here. So whatever this is will be literally the same as this. So if this was a 2, this would be a 2. If this was a 5, this would be a 5. And then you're going to get to the repeating phase finally. So this is the repeating phase. So we did the multiply. I'm sorry, we did the bring down. Multiply this value. So again, whatever number this is what this number will be. Multiply this by the number in the half box. So this is us multiplying. You'll take whatever you bring down and it gets multiplied by this. And then that result is going to go in the blank space, but one column to the right. So it goes multiply, you put the result here, and then you add. So whatever this number here is, and then whatever this other number here is, let's just say this turns into an A, you would just add these because this says to add. And then you'll get some other number here. And again, it's not the same as this number. I'm just using these symbols generically. Hashtag generic. And then you repeat. You multiply, you add, you multiply, you add, you multiply, you add, you multiply, you add until you can't multiply and add anymore. So you take this number and you'd multiply it by that number, and it would go here. And then you would add, and that number would go here. And then for this problem, we'd be done. I know it starts looking like a Madden drawing after all is said and done, but again, you've got the replay if that confused you, and you're going to see lots of examples done, so hopefully that'll help. Once completed, the far right number is the remainder. So this number right here, that is the remainder. Now, this is where things get a little weird because we're going to go from right to left. Normally we go left to right, but this is kind of like we're trying to subtract where you or add where you really need to go right to left. So this is the remainder. Then the next digit is going to be, these are going to be the coefficients of the quotient starting with your constant. So this number right here would be your constant. I just can't draw in this empty space right here, unfortunately. This number would be the coefficient of your x. If you had another number here, this would be your coefficient of your x squared. This would be your coefficient of your x cubed. And you just keep going until you run out of numbers, which in this particular problem, we ran out of numbers at the x. But again, they would just keep going, x squared, cubed, x to the fourth, if you had more numbers down there. What in the heck is this? Why are we doing, why does it work? How does it compare to long division? Because what this is, this process right here is exactly how long division flows when your denominator is specifically just x and then plus or minus a number. This is how the mechanics of long division would always work. And someone just saw a pattern to it, so they said, well, let's trim out all the x's, x squareds, and x cubes because it's a lot more to write. It's a lot more complicated on the brain, and let's just boil this down to the absolute bare bones mathematics, which is the multiplying and adding over and over and over. Now you might say, well, hold on, back in long division, it went you would divide, then you multiply, then you subtract, but now we're just multiplying and adding. What happened to the dividing? Well, the dividing part is basically just the bringing down. It's kind of a real quick assumption because there's no number in front of the x. It just reduces by a power of x every time, as we'll see. So that's the division. It's just automatic. The multiply is literally us multiplying by this number, and I may say, well, what happened to the thing in front of it? Again, that's automatically going to cancel. When we were doing the long division, we always saw the first column cancel, so we're just ignoring that. Okay, well, Mr. Beckner, that third thing, what happened to the subtraction? The subtraction is accounted for because this was a minus, and we write the opposite of that in the half box. So by changing the sign, we are essentially changing the sign when we were going from minuses to pluses or pluses to minuses. So that right there is the subtraction. So we get to skip over the division because it's automated. The multiplication, we only have to do half of it because of the other automation. And then the subtraction, we just take care of by changing one number sign instead of having to change multiple signs multiple times. These are shortcuts. These are efficiency boosters. This is an amazing technique. But again, if that denominator was 2x minus 2 or 5x minus 2 or 7x minus 2, you couldn't do this. This process would fall apart. Those shortcuts wouldn't work. Kind of like how the shortcut method of factoring only works when there's no number in front of x. It's actually a very similar style shortcut. We can't have a number in front of x. So write this down, write it down 50 times, say it 50 times, whatever you have to do to start off this memorization. But let's actually get into practicing it. We will not be seeing this remainder theorem for quite some time. Lots of examples, so let's just go ahead and bump that down. But again, change the sign of the number from the bottom that goes in the half box. Coefficients to the right of it in descending order. It has to go x to the fifth, x to the fourth, x cubed, x squared, x constant, starting with whatever the biggest one you have is. Any missing ones, you'll need zeros. Then blank space, draw a line, plus sign. Bring the first one down, multiply, put it here, add. Multiply, put it here, add. Multiply, put it here, add until you don't have any more columns. Then from right to left, it's remainder, the constant, the x coefficient, x squared coefficient, x cubed coefficient. Get the point. Let's try this out. So example 2, we are going to divide by using synthetic. So I'm telling you how to do this now on a test. If I tell you to do synthetic division and you do long division and you get the answer right, you're going to get full credit. I could certainly go back and look at your work and say you didn't follow the method and take off points, but I probably wouldn't do that. Again, trust me, you don't want to be doing long division over and 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 over in this course. A problem that should only take you a minute or two ends up taking you 5 to 10 minutes, and it is a massive time sink, and it will cause you problems for this coming test. All right, so for A, what we're going to do is we're going to borrow A from before, this x squared plus 3x minus 10 over x minus 2. We're going to do this one again, but with synthetic division. So we already know what the answer is. The answer should just be x plus 5. So if this synthetic division actually works, we'll prove it, at least by example. I wouldn't call it an official proof, but at least it'll make us feel a little better just taking a blind leap of faith. So x squared plus 3x minus 10 over x minus 2. X squared plus 3x minus 10 over x minus 2. So that's our problem. And I could write this another way. I could have written this as x squared plus 3x minus 10, division symbol, then x minus 2 in parentheses. This is literally the same problem. So please understand that if they're written this way, it's the same as that way. So again, not going to use long division. I'm not going to put the x minus 2 on the left. I'm not going to do it that way. All right, so let me just kind of zoom out so we can see the instructions as we're going for this first one at least. All right, the denominator is the appropriate format, just a variable and a plus or minus a number, with no numbers in front of the variable. So write the coefficients of the number to the right with that c½ box on the left. So this says x minus 2 in the bottom, so I don't write minus 2, I write a positive 2. That's what goes in what I'm calling a half box. And again, this is just arbitrary notation. Some people put it in a full box, but that just looks like an answer to me. That's why I like the half box. Then to the right of it, the coefficients. They are in descending order and none are missing, so we go 1 for the x squared, 3 for the 3x, and a minus 10 for the minus 10. Leave a blank row, draw a line, and a plus sign. Blank row, so leave some space, and a plus sign under the box. Bring down the first coefficient, so the 1 just gets brought down. Multiply this value by the number in the half box, put the result in the second column above the line. So it's always the first one just comes down. Then take this and you multiply it by the 2. The 1 times the 2 is going to be a 2. And I'll show the multiplication answers in red. So we just brought the 1 down. And then 1 times 2 is 2. Then we go 3 plus 2, which is 5. So we just add columns. Columns get added, and then the things on the bottom be multiplied by the number in the half box, and then go 1 to the right. Now be careful, that's not a minus 1 and a 0. It does look a little squirrely, doesn't it? That's a minus 10. So this 5, we're just repeating the process. Multiply, add until you can't anymore. So we take the 5 times the 2, which is a positive 10. And then we add negative 10 plus 10, which is 0. And there's no number here, which means we can't keep going to the right. We're done. That was insanely quick. We just did the entire long division process in seconds, in my opinion. Now, I know this being your first one, it's not going to take you seconds, but after you've done 50 of them, which you are going to do at least 50 in this course, boom, bring down the 1, multiply, add. 3 plus 2 is 5, multiply, 10, add, 0. That's it. Your entire answer is based on these numbers right here, the 1, 5, and the 0. So once you're completed, the far right number is your remainder. So I like to label below. So the 0 is the remainder. And then from right to left, these are just coefficients. 5 is the constant. Don't start at x. Start at the constant. Then the 1 is the coefficient of the x. So the answer, since there is no remainder, we don't need to put a plus 0 over x minus 2. We don't need to do that part. If there's a 0 remainder, then it's just the quotient. So that's the remainder. This says it's x plus 5 for your quotient. This right here gives us the quotient, 1x plus 5. We don't really need to write the 1. Here's the 1 if you need to see it. Again, this 1 was this 1 paired with its x, and then this 5 is because that was a 5, and that's the constant. And I don't really like to write the 1, so I'm going to delete it. This is the answer, x plus 5. Let's go back to the long division and see what we originally got. Holy cow, we got x plus 5, which we also proved by doing the factoring and reducing because this was kind of a special problem. So again, long division, all the work was here. We had to do some side work for that, and then we got our answer. And it wasn't too bad because this was just an x squared. But again, with practice, I think we can see how this is going to become more efficient because it's just multiply, add, multiply, add. There's a lot less bookkeeping, a lot less changing signs, an automated answer format. It's beautiful, it's wonderful, it's awesome. So we know that that is correct. All right, let's try another. B. X cubed minus 5x squared plus 7x minus 2, all divided by x plus 4. Now this denominator fits the ability to do synthetic division. Because there's no number in front of the x, there's no x squareds, none of that goofy business. So I can just go ahead and write that bottom number in the half box, but we don't write a 4, we write a negative 4. That's what goes in the half box. You take this and you change its sign. And again, this is a common theme that's going to keep coming up, so get used to it. Then to the right go the coefficients of the top. There are not any missing terms and they are in descending order, so the x cubed, there's a 1 in front of it, then a minus 5 for the 5x squared, minus 5x squared, then a positive 7, then a negative 2. Leave some space, draw a line with a plus sign. The first number just gets brought down. 1, and then multiply, add, multiply, add, multiply, add. For the multiplying, we take the 1 times the negative 4. This is what we multiply. And 1 times negative 4 is negative 4. And then we add. Negative 5 plus negative 4 is negative 9. And then we multiply. Negative 9 times negative 4 is positive 36. And then we add. 7 plus 36 is going to be 43. And then we multiply. 43 times negative 4. Well, 40 times 4 is 160. 4 times 3 is 12, so that'd be 172, but a negative 172. And then negative 2 plus negative 172 is negative 174. So from right to left, again, there's no more columns, so we know we're done. That is the entire long division process. Now, this is an x cubed, which means we would have gone through the long division process 3 times total. The divide, multiply, subtract. We would have divided, multiplied, and subtract 3 times, where the subtraction part, people can mess up because they might not switch both signs. The division part, you're dealing with your x to the 5th or 4x to the 5th over x and things like that, and some people can make mistakes with those. They might not reduce the powers of x, they might stumble, anything like that's possible. But here it was just very basic arithmetic over and over and over. We have to know how to format everything, that's the trick. But then from right to left, it's remainder. The 43 would be the constant. The negative 9 would be the x coefficient. And the 1 would be an x squared coefficient. So our answer would then be the 1x squared, which I will not write the 1, minus 9x plus 43. Now there is a non-zero remainder, so we need that extra bit. And it's going to go minus 174 or plus negative 174, whichever you prefer, over then the original denominator, which was x plus 4. And that's our answer. Now, we did not do this one before for example 1b when we were doing long division. This was example 1b. Now, it's not the same problem, but I'm bringing this problem up for a reason. Check out the denominator of b from the long division problem. It's 3x minus 2. Now, we said that if you want to be able to do synthetic division, this whole process hinges upon the fact that there's no number in front of the x. There's no coefficient in front of the x, which this problem has a coefficient in front of the x. So in particular, if I didn't give you instructions, use long division, use synthetic division, if I just gave you this problem and said to divide it, if you tried to use synthetic division, you can't. You can't use synthetic division because of this 3 right here. That 3 screws the whole process up. It doesn't work. It fails miserably. Trust me. If you don't trust me, then try and do this problem with synthetic division. You're not going to know what to do with the 3, first of all. When you do the process, your answer is going to vary wildly from 4x plus 3, then plus 2 over 3x minus 2. So please understand when you can and cannot use synthetic division. Now again, for the point of this course, for the 3.4, 3.5 moving forward, we're not even going to be told to do synthetic division. You're going to have to know to do it, and you're going to have to come up with the numbers to do it with. Right now, we're being told, hey, do this, hey, do that, hey, do this, do that. But in the future, because we're going to be trying to do, we're going to have a goal in mind, and to help us along with that goal, we'll have to do a whole bunch of different synthetic divisions with numbers that we come up with. I'll teach you how to come up with them, of course. But all of those will fit the synthetic division process. All right, for C, and actually what we're going to do for C is we're going to do 1C again. So this problem right here, we're going to do all over with synthetic division. Now look at how much space this took up doing it long division, and it was 1, 2, 3, 4 full revolutions of long division. Divide, multiply, subtract, divide, multiply, subtract, divide, multiply, subtract, divide, multiply, subtract. The divisions, I mean, these aren't awful things. You should know how to do these, but it's not the best thing in the world. We had missing terms, they were out of order, all sorts of complications along the way, but the main issue was Look at how much space this takes. That took us like 10 or 15 minutes to do. And that was with me at the lead. You by yourself, it might take you more than that time. So we're going to do this one synthetic division now, which it does not have a number in front of the x. I'm not saying that's a 0. I'm just saying there is no number written, which means it's a 1, which is fine. So this will fit the bill for synthetic division. So let's try it out. So we're doing, once again, 4x to the fourth plus 6x minus 4x squared. Let me do this. And all divided by x minus 4? Yes, x minus 4. So first of all, you might want to reorder this as 4x to the fourth minus 4x squared plus 6x all over x minus 4. And then you also might want to note that there are no x cubed or constant term in the top, so we're going to need zeros in their place. So when you go to do the synthetic division for this one, because it says x minus 4 in the bottom, that means a positive 4 goes in that little half box. To the right of that go the coefficients, and I'm going to do this in red. Red is wrong. First of all, if you go with the original top, if you go 4, 6, negative 4, if you go based on this is not in the correct order. This is like putting your tens before your hundreds. This is awful. This would make you tons of mistakes. All right, still red for wrong. If you do it based off of this one, you would go 4, negative 4, and 6, but this is still wrong because there are no x cubed or constant terms, and we haven't accounted for that by having missing, quote, digits. So let's finally get it right. We have the 4x to the fourth. That's this 4. This 4 is this 4. There is no x cubed term, so this represents a 0x cubed. Then we have the minus 4x squared. Then we have the plus 6x. Then there is no constant, so you need a 0 here to represent the constants. So many students miss these two details, which will make them think the problem is much shorter and simpler, and they will get a very, very wrong answer. All right, so let's draw our line, little plus sign, and now let's just bring down and then multiply, add until you're done. Bring down the 4. Multiply. 4 times 4 is 16. Add. 0 plus 16 is 16. See, if you had this negative 4 here instead of the 0, we would have gotten a 12 here, and it was already wrong. Multiply. 16 times 4 is 64. Add, and you get 60. Negative 4 plus 64 is 60. Multiply. 6 times 4 is 24, so that's 240. Add. Plus 6 is 246. Multiply. 246 times 4 is 984. Man, these numbers are sounding really familiar. 984. Add 0 plus 984 is 984. And then that's it. We, in like 30 or 40 seconds, they may take you a little longer to do the products with those bigger numbers. You are allowed calculators for this test, so you could certainly just take the calculator for 246 times 4, but I do expect you to be able to do that kind of calculation without it as well. And boom, we're done. So from right to left, that's the remainder, the constant, the coefficient of x, x squared, and x cubed. So our answer, let me just put it a little below, would be 4x cubed plus 16 x squared plus 60x plus 246 plus 984 all over the original denominator, which is x minus 4. And if you compare that to this, you get exactly the same thing without taking up this ginormous amount of space, without doing much more complicated algebra and arithmetic, without fixing your signs and having the original and your new one. It's just so much more space efficient, time efficient, everything efficient. Again, it hinges on the specific denominator. If this had been 7x minus 4, couldn't have done this process. It doesn't work. There is no shortcut if there's a number in front of the x. You'd be stuck with long division. But again, for the point of what we're going to be going through in the next coming sections, it's always synthetic division for us, always. So I love comparing 1C versus 2C because, again, it shows you those efficiencies. And by the time you get to the third one, you feel a little more well-practiced. Again, be careful. Zeros are necessary sometimes. It's not the only problem I'm going to do where that happens. Let's do another. X to the 7th minus 128, then all divided by x minus 2. And actually, before I do it, I want to point something out. Before we do D, I want to point something out because there's a pattern. Going back to A, the top originally had an x squared, and look at your answer. It has an x to the first. It's dropped by 1. Look at B. We started with an x cubed being the largest, and in the answer we have an x squared. It dropped by 1. With C, we started with an x to the fourth as the largest one, and in the answer, it dropped by 1 to x to the third. So that is another pattern that you can have in the back of your head as kind of a self-check sometimes. When you're dividing by just an x and a number, that power is always going to decrease by 1 for the largest term. If we were dividing by an x squared, they drop by 2, et cetera, et cetera. Why is that helpful? So let's say you'd gone back here and you'd done this wrong. I know by this pattern that my leading term is going to have an x cubed because I started with an x to the fourth. So let me go back and let's just do this wrong. So 4, and then let's go 4, negative 4, 6. I'm just going to say I forgot the zeros. I put everything in the right order, but I forgot my zeros. So you bring the 4 down. 4 times 4 is 16. You add, you get 12. 12 times 4 is 48. And you add, and you get 54. So what you're thinking is this is the remainder, the constant, in your coefficient of x, and you're thinking your answer will be 4x plus 12 plus 54 over x minus 4. But look at that. The leading term in your answer only has an x, whereas the original problem had an x to the fourth. It did not drop by 1, it dropped by 3, and that means that this is massively wrong. So with these synthetic division problems, you should always know, you should always assume that the answer will have a degree of 1 less than the original top. So if your division work disagrees with that, you have definitely goofed up the division work. I can promise that, as we just saw, as I'm erasing one click at a time. That generally happens when people forget a zero somewhere, whether it's 1 or 2 or 3 of them. Okay, speaking of forgetting zeros, so if you did this problem, I'm gonna do it wrong. All right, minus 2, so someone puts a positive 2 in this box. Okay, ignore a little scratch. Then x to the 7th, that's a 1, then the minus 128. Space, bring the 1 down, 1. 1 times 2 is 2, negative 128 plus 2 is negative 126. So that's your remainder and your constant. So we think the answer is 1 minus 126 over x minus 2, question mark, question mark, question mark. This started with an x to the 7th, so this should have an x to the 6th, which means we probably have a whole bunch of other terms. That is not an x to the 6th, that is a 1. That was awful because we missed a boatload of zeros. Click, click, clacky, click, clack, clicky, clack, click, clack, clack. So we need to notice that there is no x to the 6th term, x to the 5th term, x to the 4th term, x to the 3rd term, x to the 2nd, or x to the 1st. That's a lot of zeros we need. So we do put a 2 in the half box because that's a minus 2. Positive 2 goes in the half box. From right to left, x to the 7th, so that's a 1 x to the 7th. Then the x to the 6th is 0, x to the 5th, 0, x to the 4th, x to the 3rd, x to the 2nd, x, then the minus 128. Space plus sign. Problem's a lot longer than we might have thought it was. But check this out, it's going to go really quick. Bring the 1 down. 1 times 2 is 2. 0 plus 2 is 2. Multiply, add, multiply, add, multiply, add, multiply, add. It's the same thing over and over and over. 2 times 2 is 4. Add 0 and 4 and you get 4. Multiply, 4 times 2 is 8. Add 0 plus 8 is 8. Multiply times 2 is 16. We just keep doubling. That's all that's happening. Double the 16, you get 32. Add to 0 and you still get 32. Double it, you get 64. Add and you still get 64. Double it and you get 128. Add, oh, this isn't 0 plus something, it's negative 128 plus 128, which is actually 0. Well, that's kind of cool. It's always cool when the remainder is 0. As I've mentioned at least once, this is usually our goal. When we're doing the synthetic division, when we're deciding what to divide by and all that jazz, when these numbers right here are not given to us, our goal is a 0 remainder, and we'll be explaining why that is shortly. All right, so from right to left, remainder, constant, x coefficient, x squared coefficient, x cubed, x to the fourth, x to the fifth, and x to the sixth, which is one less than the original problem, so that's a good sign. So that says that our answer is 1x squared, sorry, 1x to the sixth, I don't know why I said squared, please forgive me, 1x to the sixth, plus 2x to the fifth, plus 4x to the fourth, plus 8x to the third, plus 16x squared, plus 32x, plus 64. There is no remainder, so I don't need to write plus 0 over x minus 2. That's just 0, so we just leave it off. That's our answer. There is no fractional part. So as we discussed at the beginning of this section where we had a long division problem with a 0 remainder, whenever your remainder is 0, that means that the original problem was factorable and reducible. So this is just a reminder. 0 remainder, the original factorable and reducible. I didn't need that underlined, so let's take that out. I think reducible is wrong. Oh, I spelled it the wrong way. That's why. I'm not a spelling teacher. What can I say? So that means that x to the seventh minus 128 is factorable. Now here's the thing. I'm not going to give you a formula on how to factor a septnomial. Sept meaning 7. Yeah, there is a formula out there for a binomial that's a difference of septs. And apparently the formula would involve something that kind of looks like this pattern of going up like this. Maybe that's consistent, maybe not. Maybe we could develop a formula by using this. But let's not try and go beyond our level. But the point is, this is something that's factorable via a method I have not taught you, via a method I will not teach you. However, we can implicitly factor a problem like this by doing a division. If the remainder is 0, then it means that this was factorable. It means that x to the seventh, ooh, that was weird, minus 128 is equal to x minus 2 times that x to the sixth plus all the way down to the 64. That's what that says. The only reason it says this is because if you have a over b equals to c, if you multiply both sides by b, the b's cancel, and you get that a is equal to bc. So what we had is this was our a over b, and then this in the box is our c. I just multiplied both sides by the denominator of x minus 2, and that puts it next to that thing. That's all that's happening. All right. That relates down here to this factor theorem, but before we get to the factor theorem, we need to discuss the remainder theorem. If you need to evaluate a function at a certain value c, that's what f of c means. If you need to evaluate a function at a number, and the function is complicated, you can instead divide the function by x minus c. You could use long division, but my parentheses is suggesting that you use synthetic division for the sake of time and complexity. And when you do this, the remainder is the answer. Now, this is a mind warp, I know. No one is going to look at this and go, that makes sense right now. So if I give you a function and I say, find out what f of 5 is, traditionally you would say, well, just turn all the x's into 5s and process that arithmetic and boom, you get the answer. What I'm saying is, sometimes that function is a pain in the butt to evaluate, or maybe there's some other reason. There's another hidden reason to do it that I'm not saying here. But let's just say, all right, the function's complicated and you got an x to the 20th and an x to the 15th and a square root and all this other stuff. So you go, well, all right, somebody told me one time that if I want to just plug in that 5, instead of actually plugging it in, I can do synthetic division. I could divide by x minus 5. So this is where we're deciding to divide by x minus 5. I didn't tell you to do it, we decide to. Because I want to find out what f of 5 is, I divide by x minus 5. And then when I do that synthetic division, which is pretty quick, it's a lot quicker just to multiply and add over and over than doing 5 to the 20th and 5 to the 19th and 5 to the 18th, et cetera, et cetera. Whatever you get for the remainder is the answer. Here is, we don't do a lot of proofs in this course, but here's the proof. So back when we showed our original division, the answer, we said, let's say we had some top, which I'm going to call f of x, and we divide it by x minus c. This is going to be equal to whatever your quotient is plus whatever your remainder is over x minus c. Now, what I'm saying here is, so this is just the original answer for long division or synthetic division. If you've got some top divided by a bottom, I was just trying to say this was the original top, this was the original bottom. But now I'm deciding to call the top f of x, and we're calling the bottom x minus c because it fits synthetic division. Now, in this problem here, we were not given a synthetic division problem, we were just given the function, which I'm going to call the top, and we choose to divide by x minus 5 if we're trying to evaluate at 5. All right, so check this out. Check this out. So again, the function is what we're given now. We're only given a function. We choose to divide it by x minus c. If you multiply both sides by x minus c, so I'll show that in blue. We go x minus c, and then x minus c times the f of x over x minus c equals, then that's times the quotient, and then plus times the remainder. When we do that, we see the x minus c's cancel here, and that just tells us that some function, oops, I forgot to write the remainder over the x minus c. I forgot to write that part. So these x minus c's cancel as well as these. So what this tells us is any function can be written as x minus c, some evaluation point, times the quotient plus a remainder. I know this is making your head spin. We're almost done though. All I did was I took a long division answer, I decided to clear the fractions. That was just what I did. I cleared the fractions because very often we like clearing fractions. So no more fractions. Now, here at this point, plug in c. Plug in c for the x value. So we're going to do f of c. So the x's are turning into c's. So this x here also turns into a c. And note that c minus z is 0, and 0 times q is 0. 0 times the quotient is 0. So this whole thing goes away, again, because the parentheses is 0, and then 0 times the quotient is 0. So at the end of the day, what we get is that the f of c is equal to the remainder. Holy cow. It works. It's not the longest proof in the world. It's not the simplest proof in the world. But it is a proof that if you want to do some function evaluation, you can choose to divide synthetically by x minus that number, and then whatever you get under that synthetic division for the remainder is the answer for the evaluation. Now, I know you still don't trust me with that, so when we practice one of these, we'll do a traditional plug-in, and we will do it via synthetic division to show that I'm not just making this stuff up. But again, this is an amazing theorem. This is going to be what we're using moving forward. We're going to need to do a ton of function evaluations. And first of all, they'd be a pain in the butt to do them by just plugging in x to the fourth, x to the third, x to the second, x to the first, whatever. Second of all, we're actually going to need the quotient for reasons we'll explain later. So don't think, oh, well, I don't like doing the synthetic division, so I'm just going to do the traditional evaluation anyways. You'll show that the remainder is 0 when it needs to be, but you won't have the quotient, which is something you'll need moving forward. All right, so example 3. Let's get some space. Not there. Example 3. We are going to evaluate using the remainder theorem. Do 2 of these. We'll go with A. Let's have f of x be x cubed minus 7x squared plus 5x minus 6. And again, they're going to need to be in descending order, which they are already. When we set up the synthetic division, if any were missing, we'd need a 0 in their place. And what we want to do is find f of 3, I believe. Yes. So, sure, I could certainly just go, where's my calculator not pulled out? That's weird. I've always had it out for a while. I must have had a system update overnight. No big deal. So I can certainly just go 3 to the third power, and I'm using a calculator for the saving time element, minus 7 times 3 squared plus 5 times 3 minus 6. Let me check my work. 3 cubed minus 7 times 3 squared plus 5 times 3 minus 6, and we get negative 27. So I'm telling you, classically, you could have figured out that this answer should be negative 27. But this does not give you a quotient, which again, moving forward, would be necessary. All right, so we know that f of 3 is negative 27. Let's prove it with the synthetic division. So we're going to divide by x minus 3 for synthetic division. So this is the problem that we're doing. We're taking what we originally had and we're dividing it by x minus 3, which is x cubed minus 7x squared plus 5x minus 6 all over x minus 3. Which means when we show the synthetic division, because we're dividing by x minus 3, a positive 3 goes in the half box. And here's what I want to show you. Moving forward, when we have to pull these numbers, when we're deciding that this bottom is a 3, when I don't tell you it's a 3, when you're making that decision, most people don't even show this step here. They just go straight to the synthetic division here. So check this out. This number and this number have the same sign. So finding the function evaluation, that signed number is the same sign that's going to go in the half box. It's when you're dividing, this is when the number changes sign. There's a lot of balancing that we have to do between when is it positive, when is it negative, when is it the same sign, when is it the opposite sign. So once again, practice. All right, to the right go the coefficients. 1 for the x cubed, negative 7 for the x squared, 5 for the x, and negative 6 for the constant. Draw a line, plus sign. Bring down the first number, which is a 1. Multiply. 1 times 3 is 3. Add. Negative 7 plus 3 is negative 4. Multiply. Negative 4 times 3 is negative 12. Add. 5 minus 12 is going to be negative 7. Multiply. Negative 7 times 3 is negative 21. Add. Negative 6 plus negative 21 is negative 27. Now from right to left, that's remainder, constant, coefficient of x, and x squared, but all we really need is this number, because we said that the remainder is the answer. So f of 3 is negative 27, and holy freaking cow, it's the same thing. It's not a lie. And it's all based on that proof. It's all because when you take your function, you decide to divide by that x minus c, whether it's x plus 5, x minus 7, anything like that. When you multiply it on both sides, it goes away from the remainder part, but that x minus c will be next to the quotient. But when you plug in c, it zeroes out the quotient because you'll be subtracting the same thing. But that segment won't be in the remainder because it was already in the bottom, so it canceled. Okay, so moving forward, this is not special. The fact that this answer is negative 27, that's not what we're going to want. I've already spoiled it. We're going to want it to be 0. Nope. B. So let's try another one. Let's do f of x equals x to the 4th plus 5x to the 3rd plus 5x squared minus 5, lots of 5s, 5x, and then a minus 6. And we want to find f of negative 2. That's a terrible looking 2. There we go. Better. So sure, we can just plug this negative 2 into the polynomial. But we got to be careful. I can't go negative 2 to the 4th power. This is wrong because that says it's negative 16, but because the negative 2 is inside, it's ended up being a positive 16. So you got to use your parentheses appropriately. So that's one thing you could mess up. Negative 2 to the 4th, then plus 5 times negative 2 raised to the 3rd, plus 5 times negative 2 squared, minus 5 times negative 2, minus 6. And we get 0. So this is what the answer should be. And again, moving forward, this is not what you should be doing. This is just me being safe and checking and giving you affirmation that what we're doing works. Again, you don't want to be doing this moving forward. Yes, it can show you that you get 0, but that quotient part, the stuff from the 1, the negative 4, and the negative 7 here, those are going to be necessary elements. So just doing what I did in the calculator is pointless. All right, so we're going to do this the other way. We're dividing by x plus 2. So I'm supposed to be in blue. This is the synthetic division we're doing, which means when you show it synthetically, you put a minus 2 in the half box. Again, this number is the same sign as this number. That's the convenience because that's what we're going to care about the most. Then from right to left, nothing's missing, nothing's out of order. 1, 5, 5, negative 5, negative 6. Space, plus sign. How are we on time? About 15, 20 minutes. Bring down the first number. Multiply. 1 times negative 2 is negative 2. Add. 5 minus 2 is 3. Multiply. 3 times negative 2 is negative 6. Add. 5 minus 6 is negative 1. Multiply. Negative 1 and negative 2 is positive 2. Add. Negative 5 plus 2 is negative 3. Multiply. Negative 3 times negative 2 is positive 6. Add. Negative 6 plus 6 is 0. That's the remainder. That's what we want. So f of negative 2 is equal to 0. And this is the special case we're going to want moving forward. I've already talked about how it means these things are factorable. It means the original function was factorable. So the factor theorem says if some evaluation is 0, then x minus c is a factor. Again, that just goes back down or back up to. So we had, which one do I want to use? Here we go. So we're going to start here. Let's just take this line right here before we put in a c. F of x, some function after this, the long division, can be just turned into x minus c times q plus r. So if I didn't give you a division problem, if I just gave you a function and said find its zeros, maybe, it's the same thing as taking x minus some arbitrary c, some c that we choose, but a particular c that we chose, and then times the quotient plus the remainder. Well, if the remainder is 0, since f of c is equal to 0, so if you put the c here and you get 0 and all that stuff from before, that says there is no number here, f of x is equal to x minus c times the quotient. This is a product of two things, which means it's factored. So x minus c is a factor and the quotient is a factor. It's actually a very simple proof. And then also you can just say, so is the quotient. So what that means is, example, what was that, 3b, which was x to the 4th plus 5x cubed plus 5x squared minus 5x minus 6. Because it had a 0 remainder, it was factorable, and the factored version is x minus the number we used times whatever the quotient was when we used it. We used a -2, which meant that the division was x plus 2. That's also the factor. And then the quotient was here from right to left. That was the constant, the coefficient of x, x squared, and x cubed. So it would be 1x to the 3rd plus 3x to the 2nd minus 1x minus 3. This is the strength of synthetic division right here. We have just factored a 4th order polynomial with 5 terms. And besides this, quite honestly, I have no easy way of factoring a 4th order 5-term polynomial. This is it. This is the only thing we got. Now, how did we come up with the x plus 2? Again, that's because we were dividing by x plus 2. We were evaluating at -2. If x minus, I don't want to say this. If f of c is 0, then x minus c is a factor. Just think about it this way. If you have x minus c equals 0, you add c to both sides and you get x equals c. They change sides whether you're looking at the 0 or the factor. So the 0 has one sign, the factor has another sign. Again, it's just another thing you have to keep in order. So we just factored, excuse me, hold on. So we just factored this function. Now I had to kind of push you in the right direction for now. I had to say, all right, well, let's find f of -2. And it turned out that f of -2 is 0, which is when fireworks go off and say, hey, that means if f of -2 is a 0, then x plus 2 would be the factor. If -2 is the 0, x plus 2 is the factor. And then we just use the quotient for the other part of it. And then we could take this quotient and maybe we could factor that more and more and more using this kind of arbitrary feeling factoring technique. All right. So last problem of the section. solve the equation, and let me write this out. 2x to the third minus 3x squared minus 11x plus 6 equals 0. Actually, I don't want the f of x written. It just says solve this equation given that 3 is a 0. So this is our equation. And I'm telling you that I want to find all the zeros of which there will be, whoops, I'm on eraser. Don't do that. Because this is a 3, that means that there are 3 possible zeros. There might be a multiplicity of them, but there are 3 zeros. They could be imaginary, but there are 3 zeros. And I'm telling you one of them because you look at this and you go, okay, well, we can't use the quadratic formula because that's a cubic, so that's out. And you might go, oh, let's try and factor it. It's got 4 terms, so factor by grouping. Well, factor by grouping fails here. There is no GCF from the first pair that after you take it from the second pair. Let me say this a little more specifically. The GCF of x squared, when you take that from the first, will not match the second one because there is no GCF of the second, so you pop out a 1, a negative 1 specifically. That would be 11x minus 6. This would be 2x minus 3. They don't match, which means you can't factor by grouping. So there is no traditional factoring method for this problem, which means we're going to have to go to this kind of new non-traditional way of factoring that involves synthetic division, knowing zeros and such. However, this time, we told you that 3 is a 0, which means you don't have to do the synthetic division. If 3 is a 0, wrong color, since x equals 3 is a 0, x minus 3 is a factor. We don't have to do the synthetic division to know that. That doesn't mean we don't have to do the synthetic division, though. I was trying to choose my words carefully. If x equals 3 is a 0, that means x minus 3 is a factor. So that means that this right here can be written as x minus 3 times something else. But the question is, what is this something else? Well, the factor theorem says that it's the quotient whenever you do your synthetic division. So, oh, shoot, we do need to do that synthetic division. That's what I was talking about earlier, where just because you know it spits out a 0, even if you do the traditional evaluation, like I was showing on the calculator, it doesn't give you the quotient. You still have to fall back on division. You could do long division, but it's time consuming. Trust me, do synthetic division. So we need a quotient. So in order to find the quotient, we got to do the division. We got to take this original polynomial and divide it by something. So we're going to do 2x cubed minus 3x squared minus 11x plus 6. And we're going to divide it by, we told you that 3 is a 0, so that means we're dividing by x minus 3. The factor and what we divide by match. The 0 and the number that go in the half box match. The 0 and the number that go in the box match. But again, come on, undo. The denominator and the factor match. All right, so to the right, we go 2, negative 3, negative 11, 6, leave some space, plus sign, bring her down, 2. 2 times 3 is 6. I'm going to stop changing color. Negative 3 plus 6 is going to be positive 3. 3 times 3 is 9. 11. Negative 11 plus 9 is negative 2. Negative 2 times 3 is negative 6. Negative 6 plus 6 is 0. So that confirms. Now, you were trusting me that 3 was a 0. I told you that, but maybe you don't trust me. Well, this confirms it. Also, if you plugged in just a 3 here, 3 cubed is 8. Why did I just say 8? Excuse me. 3 cubed is 27 times 2 is 54, yada, yada, yada. It will prove that that's a 0. But now what we have from right to left is the remainder, the constant, the coefficient of x and x squared. So we can say that the quotient is 2x squared plus 3x minus 2, which means 2x cubed minus 3x squared minus 11x plus 6 equals 0 will become the x minus 3, that was the factor, because 3 was a 0, x minus 3 is the factor, times the quotient, which was the 2 What happened? Why is my pen not working? There's no batteries. There we go. Technology, man. 2x squared plus 3x minus 2 equals 0. Now, our goal for this was to find all the zeros to solve this equation. Or I could have just said, given f of x, find all its zeros, which would mean you were setting it equal to 0. I can phrase it differently. Well, we already know that this part, this x minus 3, leads to 3 being a 0. We don't need to focus on that anymore. We just need to focus on this bit, which is quadratic, so maybe it's factorable. Maybe, maybe not. It's going to depend from problem to problem. You may need the quadratic formula here. But I don't think we do this time. If you just want to say, all right, 2 and 2, 2 times 2 is 4. So for your AC, that's negative 4, which is 1 times 4, 2 times 2. We need to find a pair that subtracts to 3, which would be the 1 and the 4. And you need the 4 to be positive and the 3 to be negative. You can go through with all that process. But because the A and the C are just 2's, it's very easy to figure out these setups. The 2x squared means this has to be a 2x and this has to be an x. For this number being a minus 2, it just means that it might go 1 and 2 here, oops, or it might be the other way around. It might be a 2 here and a 1 here. Well, it's going to be a 1 and a 2. I'm just skipping the trial and error segment because then the outer is your 4 that you need. Your inner is the 1 that you need. Those will always match the AC choice. But we need the product to come out, the larger product to come out positive. So we need this to be the plus 2 and this to be a minus. And that's equal to 0. Now this is completely factored. So we just set each factor equal to 0. The first one tells us what we already know, that x equals 3. The second one, add 1 to both sides, you get 2x equals 1, divide by 2, and you get x equals a half. For the x plus 2 equals 0, we get x equals negative 2. We get all 3 of our zeros. We have just factored via a non-traditional factoring method to get zeros, and kind of a non-traditional up to this point way. This is a way of factoring any polynomial that has rational zeros. Now, for this problem, I told you at the beginning what one of the zeros was. So in this section, we say, okay, well, you got to give me one of them. You got to give me at least one so I can move on. Guess what? In the next section, we don't do that anymore. We go solve the equation. That's it. We would not give you this anymore in 3.4. We'll just say solve that equation, or I'll say this is your f of x, find its zeros. So I wouldn't have said the equals 0 part. You'd have to know to do that. So how in the world do you come up with this 3 being a 0? Or maybe you figured out that the negative 2 is a 0, or maybe you figured out that the half is a 0. How do you find one of these to then chug along to get to something that you can inevitably factor, or maybe just keep doing this synthetic division process over and over and over? Come on. I hit redo there, didn't I? That's fine. That's fine. Okay, good enough. And we have 1 minute left, so we are definitely not going to start 3.4. But that is what we'll be doing. 3.4, we are primarily going to focus on just being given a function and being told to find all of its zeros, which means to factor it as much as possible. And we're going to have to come up with a method to decide what to do the synthetic division with to ultimately hope for a 0 so that we get a quotient, and then we can boil this down to something simpler and something simpler and something simpler. Picking these numbers is not that difficult. We're going to be given a list. We'll have a constructive way to determine that list, and then you just find one that spits out a 0 remainder. So you will be doing maybe 3 or 4 or 5 or 6 or 7 or 8 synthetic divisions in one problem, just doing one until you get a remainder of 0. So the first one you do might not be 0, so then you do another, then you do another, then you do another. We can use technology to give us hints as to which ones will work. That way we don't do 20 or 30 without getting anywhere. That would be a pain in the butt and frustrating. So we can use our graphing calculator, say, here's one that works, but then you still have to show all the synthetic division because you still need to show the quotient. You still have to show your work for a test. I would not give you full credit for just answers and no work for this stuff. But we're going to call it a day there. That is 3.3, so that
So that due date will be in 1 week, which will be the 15th. And then obviously we already knew what our 3.2 due date was, which was the 13th. And then next time we'll get into 3.4. And if we finish it, it'll be due a week after that. And yeah, so besides that, if you have any questions, per usual, you can email me. We'll start talking about the Chapter 3 test soon-ish, but it's still on the horizon since we've just finished the first 3 sections. There are not 8 sections to this chapter. I think we're only going to cover 6 of them. That sounds right, where if you remember, we actually did a section from Chapter 3 back in Chapter 1 because it was what I like to call misappropriated. It was in the wrong spot. So yeah, we'll have about 6 sections, not including that one, because there's still more than 6 sections in Chapter 3. All right, so again, if you have any questions, please email me. But besides that, have a good day, have a good weekend, be productive, and we'll see you next week.